Picture this. It's 8 a.m. in a major metropolis, right at the peak of rush hour. The sidewalks are overflowing, delivery trucks are double parked everywhere, and every single surface street is just choked with bumper-to-bumper traffic. Millions of people need to get to work or school at the exact same time. If we all had to rely purely on cars and buses, the sheer volume of humanity would bring the entire city to a grinding, smog-filled standstill. It would be absolute gridlock. So how exactly do we solve this? How is an everyday commute orchestrated for millions of people right beneath our feet every single day without devolving into total chaos?
Well, welcome to this explainer. Today we're going to explore the subway as if it were a massive, living, breathing organism. It's honestly one of the most efficient urban transportation systems ever created, and the way its physical and digital components just work together seamlessly is nothing short of an engineering marvel. To really wrap our heads around it, we're going to map out this anatomy. The tunnels, they act as the deep structural skeleton. The massive electrical systems pump like lifeblood, giving it muscle. And the invisible signaling networks, they function as a highly advanced brain and nervous system.
So here's the game plan for our blueprint today. 1. Tunnels and tracks. 2. Powering the commute. 3. Recapturing energy. 4. The nervous system. And 5. Stations and safety. Let's build our mental model from the dirt all the way up to the digital signals.
Starting with Section 1. Digging deep, tunnels and tracks. Let's look at the skeleton of the system.
Historically, engineers relied heavily on what's known as the cut-and-cover method. Try to imagine living through this. They would literally dig a massive, chaotic trench right down the middle of a major avenue. It meant tearing up water mains, navigating tangled gas lines, and shutting down entire streets for years at a time just to build a tunnel and pave back over it. A total logistical nightmare. Now contrast that incredibly disruptive reality with the silent magic of modern deep tunnel boring. It glides through bedrock far, far below, avoiding surface disruption completely.
And a modern tunnel boring machine, or TBM, isn't just a giant drill. It's a massive, self-contained, moving underground factory. You have this huge rotating cutter head at the front, slowly excavating the rock. But how does it move forward? Well, incredibly powerful hydraulic jacks push against precast concrete rings that the machine literally just finished laying down. It inches forward, clears out the debris, and then robotic arms install the next perfect ring of concrete right there in the dark. It basically chews through the earth and leaves a fully stabilized, perfectly round tunnel behind it. But engineers can't just use a one-size-fits-all machine for this. Urban geology is insanely complex. If you try to use a heavy, hard rock drill in soft, wet mud, the vibrations could cause the entire tunnel ceiling to collapse on you. And obviously, if you send a soft earth machine into solid granite, the cutter head will just shatter. So depending on the local geology, engineers deploy highly specialized TBMs to safely navigate those extremes, often using mixed shield machines for those tricky transitional zones, where the earth changes from soft clay to solid bedrock in a matter of feet.
All right, moving on to Section 2, powering the commute. Electricity and traction. Let's see what gives this organism its muscle.
First off, subways absolutely have to run on clean electricity. If they use diesel, the exhaust gases would rapidly accumulate in those tight tubes, making them totally unbreathable. Instead, power is delivered directly through a dedicated third rail. To picture how this works, think back to an electric slot car set you might have played with as a kid. Just like those toy cars have little metal brushes dragging along the track to pull electricity, a real subway train has a heavy metal contact shoe that physically slides along that electrified third rail, pulling immense amounts of power straight into the motors.
Now you might be wondering, why don't subways just use the overhead power wires we see on light rail or traditional trains? Well, it all comes down to space and money. Digging a tunnel even just 2 or 3 feet taller to safely fit high-voltage overhead wires across a whole city network would mean removing millions of additional tons of earth. We're talking billions of extra dollars. So the third rail, which caps out around 1200 volts DC, requires way less vertical clearance. It's the undisputed champion for tight subway tunnels.
Which brings us to Section 3, recapturing energy, regenerative braking. This is one of the coolest hidden features of modern transit.
Through regenerative braking, a decelerating train actually becomes a temporary power plant. It's the exact same concept that recharges the battery in a hybrid car, like Prius, when you're coasting down a steep hill, just scaled up massively. Instead of turning the momentum of a 400-ton metal tube into useless heat and wearing out physical brake pads, the electric traction motors essentially run in reverse. They act as generators, converting all that kinetic energy back into electrical energy and pushing it right back into the third rail for another train nearby to use instantly.
Engineers knew this worked great in theory, but they needed to know exactly how much energy it was actually saving on a massive scale. So
they did something kind of drastic. In a collaborative study with Con Edison and New York City Transit on the 7 line, they actually turned off the regenerative braking capability on all the trains for a while, just to definitively measure the impact on the local power grid. And the results? Absolutely staggering. The study proved that capturing this energy results in an incredible 8% total energy savings. That equated to 32.4 megawatt-hours saved. To put that into perspective for you, that is roughly enough electricity to power your house for over 3 entire years. And it's saved entirely just by trains routinely hitting the brakes as they approach a station. It literally turns your daily commute into an eco-friendly powerhouse.
Let's jump to Section 4, the nervous system, train signaling, and CBTC. This is how central control safely orchestrates everything.
So legacy systems rely on something called fixed block signaling. This is essentially like driving on a highway completely blindfolded, where you only get a radio update every mile telling you if there's a car somewhere ahead of you. Because the old system only knew a train was somewhere within a static 1,000-foot block of track, it required these huge, inefficient safety gaps between trains. But modern transit uses communications-based train control, or CBTC. It's basically a real-time GPS map. It uses wireless radio signals to precisely track a moving train's exact position, speed, and braking distance, wrapping a really tight dynamic safety buffer around it.
And here is the real game changer for urban transit. The solution to overcrowded platforms isn't always spending decades digging more tunnels. Sometimes you literally just need a software upgrade. By switching to this wireless communication network, central control can safely pack trains much closer together, running them at intervals of less than 90 seconds. This directly translates to a faster, smoother, and far less crowded commute for us.
Let's wrap up our anatomy lesson with Section 5. Stations, ventilation, and safety, the respiratory and immune systems. Stations are where this highly technical system seamlessly meets everyday urban life. Depending on the local geography, they use either island or side platforms. And engineers don't just pick these at random. An island platform, which sits right between two tracks, might be used to save on excavation space in a narrow street. A side platform, on the other hand, might be completely necessary if tracks need to be split wide apart to dodge a massive central building foundation or an unmovable utility line. Basically, the constraints of the city above dictate the entire design below.
Now, because these systems operate entirely underground, air quality is a huge deal. Massive industrial fans serve as the lungs of the subway. But actually, before the fans even kick in, the transit system relies heavily on the piston effect. The trains themselves act like giant plungers. As they speed through those tight cylindrical tunnels, they push a massive wall of stale air out of the street grates ahead of them and simultaneously pull a vacuum of fresh air down into the stations right behind them.
And when mechanical ventilation is required, the sheer scale of the engineering is just mind-blowing. The upgraded ventilation planned for New York City moves a staggering 600,000 cubic feet of fresh air every single minute. To visualize that, it's the equivalent of moving almost 7 entire Olympic-sized swimming pools full of air every 60 seconds. That is the immense volume required just to keep things breathable down there.
Finally, the immune system. Safety. The whole network is built with immense, overlapping redundancies. Some are highly digital, like platform screen doors, while others are wonderfully analog. Take the physical trip arm, for example. If a train somehow runs a red stop signal, a literal metal arm mounted on the tracks physically swings up, strikes a lever under the passing train, and forcefully bleeds the train's air brakes, bringing it to an immediate halt. It's a brilliantly simple, totally unhackable failsafe designed to protect you no matter what. We really take the subway for granted, don't we? We usually just view it as a backdrop for our daily routines. But the next time you swipe your card, put your headphones in, and stand on that platform, take a quick moment to look around. Realize that you are actually traveling straight through the veins of one of the most complex, finely tuned living machines humanity has ever built. Look for that third rail, listen for the massive ventilation fans acting as lungs, and just appreciate the monumental engineering making your journey possible. Thanks for joining me on this explainer, and keep learning.